Okay, we're going to start 14.4, which is the last section for the course here. It says that a graph is a tree if the graph is connected and contains no circuits. So 31, determine if each graph is a tree. Well, it's connected. It contains no circuits. So yes, that would be a tree. This one is not connected. I got two parts there. And this one contains a circuit. Okay? So that's not a tree. Problem 32 says determine whether the graph described must be a tree. Okay, part A, an instructor in an algebra class is deciding on what material should be on the first test. He decides that the test will cover chapters 1, 2, and 3. In chapter 1, the students will be tested over sections 1 and 3. In chapter 2, the students will be tested over sections 2.1, 2.2, and 2.4. In chapter 3, the students will be tested over 3.1 and 3.2. He draws a graph with the vertex representing test 1 and the additional vertices representing each chapter along with each section to know for the test. Okay, so here's a diagram that I drew, yeah, that would be a tree then, okay, since the graph is connected and it contains no circuits. Okay. Part B, a power generator at a dam is to power a distribution center. The generator can send 300 megawatts to substation 1, 200 megawatts to substation 2, and 250 megawatts to substation 3. In addition, substation 2 can send 100 megawatts to substation 1 and 70 megawatts to substation 3. Substation 1 can send at most 280 megawatts to the distribution center, and substation 3 can send at most 300 megawatts to the distribution center. A graph is drawn with the vertices representing the dam, each substation, and the distribution center. The edges represent the amount of megawatts that can be sent from the first vertex to the second vertex. So this is not a tree, right? Because there's circuits involved. Okay, we got a few circuits there. Okay. Another definition, a spanning tree for a graph is a tree that results from the removal of as many edges as possible from the original graph without making it disconnected. Okay, problem 33. We're going to find two different spanning trees for the graph. There may be different correct answers. Okay, there's several answers for this one. But you want to have each vertice on the graph labeled. And of course, make sure that there's an edge connecting. Okay, so I'm not going to have an edge, connecting A to D because I don't see that on the original graph. Okay, so I'm basically just going to remove edges and end up with a tree. Okay, so here'd be one example of that, and here'd be another example of that. Okay, so I'm removing edges there, and I end up with a tree. Okay. There are many different trees possible for this graph. Okay. Now, by the way, one mistake that I seem to always see here is that a student thinks that we're just drawing a tree, which we are just drawing a tree, but we're removing the edges that are currently there. We are not adding whatever edge we please. Okay, so like there's no edge from A to C. There's no edge from A to E. There's no edge from A to D. Okay, so I'm not adding edges wherever I please. It's got to be edges already on the graph. Problem 34 says that if a connected graph has circuits, none of which have common edges, then the number of spanning trees for the graph is the product of the number of edges in all the circuits. Determine how many spanning trees each graph has. Okay, so here's a circuit. There's 4 edges, and here's another circuit. Here's 3 edges, so 4 times 3 gives us 12 spanning trees total would be on this graph. For this one, here's 3 edges, okay, and here's another one with 3 edges, so 3 times 3 is 9 spanning trees that would be possible for this graph. Okay. Definition: a minimum spanning tree for a weighted graph is the spanning tree for that graph that has the smallest possible sum of the weights. Okay, so definition 1, algorithm for finding a minimum spanning tree for a connected weighted graph is called Kruskal's algorithm. The steps for using the algorithm are below. Okay, so step 1, we're going to choose the edge with the lowest weight. If more than one edge could be selected, then pick either one. It's not going to matter. Step 2, we're going to choose another edge from those not yet selected with the least lowest weight, with the next lowest weight, excuse me. Okay. Step 3, we're going to continue to choose an edge of the next lowest weight from those not yet selected that does not form a circuit with any of the edges already selected. Okay, and step 4, I'm going to repeat step 3 until all the vertices have been connected. Okay, so problem 35 there. I want to use Kruskal's algorithm to find a spanning tree, find the total weight of this minimum spanning tree. Okay, so I've drawn the tree here, and I've kept track of the total weight. Okay, so the first branch that I select is B to F. Okay, since that has the lowest weight out of any of them. Okay, and I'm keeping track of the weights, like I said. The next one is CD. Okay, so there's CD. Okay, I got BF and CD. The next one is AE. Okay, so I've selected that one. The next one is FD. Okay, which is that one. And the next one is I can't use BC because that's going to form a circuit. I can't use FC because that's going to form a circuit. So that's the thing with forming a tree is you got to be aware of forming circuits too. So AF has got a measure of 5 units, and so this ends up being 1 plus 2 plus 3 plus 4 plus 5, which gives us a total weight of 15. Okay. Now there's a note there saying that we might get a different minimum spanning tree if we were told to begin at a specific edge. Okay, so with this one I just saw 1 BF, and that's so I started there. But if I were told to start at like FD, well, it's possible that I might get a different spanning tree. Okay. Problem 36 is given there. A school consists of 6 separate buildings represented by the vertices in the graph. The paths between some of the buildings are shown below. The graph also shows the length and feet of each path. Okay. School administrators want to cover some of these paths with roofs so that the students will be able to walk between buildings without getting wet when it rains. To minimize the cost, they select paths to be covered such that the total length to be covered is as small as possible. Okay, so I don't want to be wasting money. Okay, use Kruskal's algorithm to determine which paths to cover. Also determine the total length of the pathways to be covered. Okay, so this problem here is going to be pretty much the same thing as what we just did. So I got a graph, and I'm finding a minimum spanning tree for the graph, and I'm also keeping track of the total weight. Okay, well, let's see here. So if I select an edge there with minimum weight, BE, would be my start point there. Okay, and let's see, here's BF. Okay, FD. And BF and FD have the same weight, so it's not going to matter which one I select first. I could have selected FD first and then BF second. Okay, let's see here. So I can't select EF, right, because that's going to form a circuit there. I can't select ED because that's going to form another circuit. So AD is going to measure of 32 when we select that one. Okay, and then DC has a measure of 35. Okay, so if you add up those numbers there, 137 would be the total length to be covered there. So the school would want to form a structure with the least amount of cost using this particular model. Okay. Problem 37. A tree with n-1 vertices has n-1, or excuse me, a tree with n vertices has n-1 edges. Okay. How many vertices are there with a tree, in a tree with 40 edges? Okay, so there's 40 edges, there'd be 41 vertices. Okay, sometimes students have these switched. Problem 38. A business has 24 employees, each with his or her own desk computer, all working in the same office. The managers want to network the computers, so they decide to they need to install cables between individual computers so that every computer is linked to the network. Because of the way that the office is laid out, it is not convenient to simply connect all the computers in one long line. Determine the least number of cables the managers need to install to achieve their objective. Okay, so basically the thing to see here is that you got 24 employees, right? So that'd be 24 vertices. There'd be 23 cables there, each kind of wiring the network in the office there together. Okay. The homework in this section is on page 853, so be sure to look at those problems. This is in 14.4. We're now done with the course, so you know, if you need to review anything, that's fine. And here's your last homework assignment there. Okay.